Section: Introduction. In this section, we discuss the importance of embedding models in search and retrieval augmented generation (RAG) tasks. Unlike traditional keyword search, embedding models can understand queries like, "How tall is Tom Cruise?" and "Height of the actor who plays Maverick in Top Gun," even if they don't share common words. The open source and research community has been continuously improving text embedding models like E5, GTE, and GINA, thanks to large-scale evaluation benchmarks like MSMARCO, BEIR, and MTEB. Our work began in early 2024 due to the lack of efficient open text embedding models that could compete with closed-source models like Cohere's Embed v3 or OpenAI's Text Embed 3 Large. While models like SFR Embedding Mistral and Grit-LM perform well, their large size and dimensionality make them impractical for many real-world applications. To address this, we aim to create high-quality embedding models with fewer parameters. Through data-centric experiments, we developed the Arctic family of text embedding models, optimizing them for retrieval performance on the MTEB leaderboard. Each model in the suite achieved state-of-the-art performance for its size, as shown in our technical report. Our contributions include releasing the Arctic-Embed models under a permissive license, demonstrating the importance of data organization for retrieval quality, and introducing a novel query generation technique based on mined-hard negatives. In the background, we explain how embedding models map variable inputs to fixed-dimensional vectors, focusing on text embeddings for retrieval tasks. In related work, we discuss training approaches using supervised learning with positive and negative document query pairs, the importance of model architecture like transformers, and the shift towards contrastive loss functions for training embedding models. Section Summary. In this section, we introduce the significance of embedding models in search and retrieval augmented generation (RAG) tasks, highlighting their ability to encode information beyond token overlap for accurate retrieval. We discuss the motivation behind developing the Arctic family of text embedding models, aiming to provide high-quality retrieval models with fewer parameters compared to existing closed-source models. Our work focuses on optimizing retrieval performance through data-centric experiments and novel techniques for query generation, ultimately achieving state-of-the-art results on the MTEB retrieval leaderboard. Section: Arctic-Embed. In this section, we aim to develop the Arctic-Embed model by following the best practices in the existing literature. Similar to previous works such as E5, BGE, GTE, GINA, and Nomic, we conducted 2 training rounds using different datasets. The first round involved large-scale pre-training with in-batch negative examples, focusing on pairs of queries and relevant documents. The second round, known as fine-tuning, included pairs of queries and documents along with hard, negative documents. We used a negative mining strategy to create a dataset of about 1 million samples for this round. Our approach closely followed previous works but resulted in models that outperformed them on the MTEB retrieval benchmark. We analyzed potential reasons for this improved performance in the comparison table and conducted ablation studies to test these hypotheses. We trained models of various sizes using BERT-like backbones, including standard BERT architectures, BERT base and large, mini LMV2 for smaller sizes, and Nomic BERT for long context variants. In terms of architecture, we did not modify the base model but used the final hidden state of the CLS token as the embedding vector instead of pooling output vectors. This decision was influenced by previous studies showing improved performance on the semantic text similarity evaluation. For training data, we drew inspiration from large language models, LLMs, and employed filtering methods from Refined Web, C4, Gopher, and Together AI. We applied quality and consistency filters to create a curated dataset by removing low-quality or irrelevant documents. We also used a pair similarity consistency filter based on sentence similarity to ensure the pairs were semantically similar. Due to the differences in dataset characteristics, we did not simply concatenate all datasets but instead conducted experiments to understand their impact on performance. We combined datasets based on their relative performance in these experiments. Our pre-training dataset consisted of 308 million query document pairs, while our fine-tuning dataset included around 1 million pairs from web search data and public datasets like Hotpot QA and NQ. We excluded certain public datasets from our mix due to their lower usefulness in terms of positive pair consistency and negative pair hardness. We observed that quality was more important than quantity during the fine-tuning phase to avoid lower quality models. Section Summary. In this section, we aim to develop the Arctic-Embed model by training an embedding model from scratch based on existing best practices. We conducted 2 training rounds using different datasets, with the first round focusing on large-scale pre-training and the second round involving fine-tuning with additional challenging negative documents. Our approach, which included training models of varying sizes and utilizing the final hidden state of the CLS token as the embedding vector, led to improved performance on the MTEB retrieval benchmark compared to prior works. Section: Synthetic data for semantic dense mining. In this section, we explored ways to enhance our model's performance through the use of synthetic data and tunable hard negative mining. We found that while web-scale data is abundant for pre-training, high-quality examples for fine-tuning are limited. To tackle this issue, we created synthetic data to supplement our datasets, which significantly improved downstream performance. We utilized large language models to generate new queries, but we also included negative documents in our inputs to ensure the generated queries were grounded. By doing this, we were able to improve the quality of our synthetic data. Our approach, as illustrated in Fig. Hotpot synthetic, led to score increases comparable to those achieved with the original Hotpot QA dataset. When it comes to fine-tuning, we considered the importance of including hard, negative examples in the training datasets. We developed a tunable hard negative mining strategy where we used a text embedding model to identify and score the most challenging negatives for each training example. By setting a score threshold, we could filter out these hard negatives. Through experimentation, we determined that using an upper threshold was more effective than a specific rank, as it accounted for variations in query difficulty. Additionally, we explored the impact of ordering data by the difficulty of negatives, known as curriculum learning, which showed promising results in improving model performance. Although we did not use this approach in training our published models, it demonstrated potential for enhancing the learning process. Furthermore, we discussed the significance of model initialization, highlighting the benefits of starting from a well pre-trained language model. Our experiments indicated that using pre-trained models specifically designed for information retrieval could positively influence performance. In our large-scale contrastive pre-training with in-batch negatives, we emphasized the importance of batch size and dataset scale. By training with in-batch negatives and optimizing learning rate schedules, we observed improvements in model performance. Additionally, we found that using longer truncation lengths for documents during training led to better retrieval performance. Lastly, we discussed the strategy of source stratification, where each batch during pre-training contains data from a single source. This approach significantly improved model quality, as indicated by our ablation studies. Section Summary. In this section, we utilized synthetic data creation to address the scarcity of high-quality examples for fine-tuning, generating additional datasets that improved downstream performance significantly. We implemented a tunable hard negative mining strategy to identify and discard the hardest negatives for each training example, optimizing the learning process. Additionally, we leveraged a pre-trained language model for model initialization, preferring permissibly licensed base models for better performance, and observed that starting from a thoroughly trained base model enhanced sample efficiency and convergence speed during experimentation. Section: Quality-focused contrastive training with curated negatives. In this section, we conduct a second round of training after extensive training by utilizing a fine-tuning dataset with clearly labeled negative examples. We do not use a learning rate warm-up but follow the same linear learning rate decay schedule as in the initial training phase. We limit the sequence lengths to 512 for both queries and documents across all models, including the M-long variant for long context. Each batch includes 1 positive document and 10 challenging negative documents for every query. The batch sizes and learning rates for each model size can be found in the hyperparameters table. After some initial fine-tuning runs, we discovered that turning off in-batch negative loss did not noticeably harm performance. Therefore, we stopped using in-batch negatives during fine-tuning to simplify the tuning process, especially since the relationship between batch size and in-batch loss is complex. To enhance our experimental efficiency, iteration speed, and maximum feasible batch size, we optimized our training setup within our computational constraints. We focused on maximizing training and iteration efficiency, assuming a single training node with 8 NVIDIA H100 GPUs. By implementing a custom data loader and writing our training loop in plain PyTorch, we were able to achieve high efficiency. We also identified and removed performance bottlenecks through benchmarking, ensuring optimal throughput and GPU utilization. We evaluated the model performance on the retrieval section of the MTEB dataset to assess our retrieval quality. The summarized results of the MTEB experiments are presented in a figure, and a detailed breakdown by dataset can be found in the full table in the appendix. Additionally, we evaluated the performance of our long context model using the LOCO benchmark. For our initial Arctic-Embed release, we did not specifically tailor our training approach for long context support. Despite this, our M-long variant, trained on short sequence data, performed reasonably well on long context benchmark datasets. While it may not be the top choice for long sequences, its strong MTEB retrieval scores suggest it could be suitable for datasets with a mix of long and short sequences. We conducted various ablation studies to test hypotheses regarding the factors influencing the higher MTEB retrieval scores of Arctic-Embed compared to similar models. These studies examined the effects of batch size, sequence length, base model, and training data on model performance. The results supported our hypotheses about the impact of data sourcing, longer sequence length, and source stratification on model performance. Additionally, we observed that source stratification became more crucial later in training compared to factors like batch size. Section Summary. In this section, we perform a second round of training using explicitly labeled negative examples after large-scale training. We optimize our training setup for efficiency, focusing on maximizing experimental throughput and iteration speed within our computational budget. Additionally, we conducted ablation studies to investigate factors influencing model performance, such as batch size, sequence length, and source stratification, with results supporting the importance of these aspects in improving retrieval quality. Section: End-to-end ablations. In this section, we thoroughly studied the impact of training data on the final score by extending a subset of our pre-training ablation study through the fine-tuning step. We performed a fine-tuning step similar to the one used on our published Arctic-Embed M model on different data and base model configurations A, B, and C. The pre-training and fine-tuning progressions can be seen in a figure, with the final MTEB retrieval scores presented in a table. Despite a small performance difference between models pre-trained with Snowflake and Nomic data during pre-training, the gap significantly increased during fine-tuning, even though the fine-tuning process remained the same. There was also a slight enhancement in the final score for the configuration utilizing E5 unsupervised base. It is important to mention that adjusting the fine-tuning step to an E5 unsupervised base model pre-trained on our data might have influenced these outcomes.